what I understood from yesterday's class was, there was some lagging in the definitions that, uh, you know, I had asked you guys to look at in from Raj Jain's book. So this is a few notes that I have from the particular book. So I will start with that and then I will continue with analysis of a single queue. Okay. So let me just go through it very quickly. So I have already given you the definition of what a stochastic process is. So this is the formal definition that is there on the slide, as you can see. So a stochastic process is a family of random variables given by xt such that t belongs to capital T, where t is an index set and t can be either discrete or continuous. So the values that are assumed by xt, they are called as states, and the state space I is said to be the set of all possible states. And this stochastic process can also sometimes be called as a random process, or it can also be called as the chance process. Okay, so it means the same. Whenever somebody is talking about stochastic process, they can also call them by these two names. Okay, so after this, there are different types of stochastic processes. Okay, so two of them you already know, that is discrete state and continuous state processes. Okay, so how do you define discrete and continuous state? So for discrete state, you know that if they are finite or countable states, then you call them as discrete states. And if they are, they can take any real value, that means you cannot count them as such. So then you call them as continuous state processes. Okay, so it basically depends on the values that its state can take. Okay. So these are known as discrete and continuous state processes. And this is an example that has been given for a discrete state process. For example, jobs in a system denoted by NT can only take values which are countable, that is 0, 1, 2, and so on. So it is called as discrete state process, and it is also called as a stochastic chain. And continuous state process, an example has been given, that is the waiting time which can take any real value for a particular state. So this is known as a continuous state process. All right. Now let's come to a second type of stochastic process, that is known as Markov process. So we know about the Markovian property, right? So what is it? So here, how do we define a Markov process? So if future states depend only on the present state and are independent of the past, then we call them as Markov processes. Okay, so we use it, as I've already told you, that this kind of property is very useful in case of analysis. Okay, so this makes it easier to analyze because you don't have to look at the past. Okay, you don't have to look at what has happened in the past. Only dependent on the present state, you will analyze the system. Okay, so these kind of processes are very helpful in case of analysis. Then comes a third type of stochastic process, which also we have taken a look yesterday, which is known as birth-death process. It is also a kind of Markov process, but in this kind of process, the transitions, the state transitions, are restricted to only neighboring states. Right, so yesterday's class we had seen that the transitions were only restricted to either the next state, or there was a transition that was happening from the next state to the previous state, or the current state to the previous state. Okay, so we were seeing that either there is no arrival or no departure, so the transition was happening in the same state only, right? That is the probability of staying in that same state. So that also we have seen. Then we saw that, okay, otherwise what is happening, that either you are going to the next state, that is known as a birth. That means there was an arrival, so therefore you went to the next state. So there was a birth, and when there was a departure, you came or you went to the previous state. Okay, so there was a death. Okay, so how do we represent it? So we represent the states by integers. We have seen it in the last class. So if you are at the nth state, you can either go to the n plus 1th state with a birth, or you can go to the n minus 1th state with a death. Okay, so here an example has been given, that is jobs in a queue with single server can be represented by a birth-death process. We have already seen that the jobs in a queue could be represented by a birth-death process in a single server. Now, as you can see that the arrival or a birth causes the state to change by +1, and the departure after a service, which is known as a death, causes the state to change by -1. Okay, so now this can happen only if the jobs are arriving individually, right? Not in batch. If it happens in batches, then it becomes difficult. Na? You cannot I mean, it will be difficult to first go to a particular state, right? Because you are transitioning to only neighboring states, right? So that means only with one arrival, you will go to a neighboring state. So this is a condition that you have in birth-death process, that you are not having any batch arrivals. You are having only individual arrivals. Okay. So this is about birth-death processes. Now, another type of stochastic process that we would need is Poisson processes. We have already studied about Poisson processes and its properties. So I will not get into Poisson and its different properties. Just the thing that if the inter-arrival times are IID and they are exponentially distributed, then the number of arrivals over an interval, over a time interval, we say that it has a Poisson distribution, and it is known as a Poisson process. Okay, so because arrivals are memoryless, it makes it pretty easy to analyze a system when we assume that the arrivals are following a Poisson process. Okay, so merging of Poisson streams and splitting of Poisson processes we have already studied. So I will not get into this any further. What I will do is I will go to the part that I was telling you about yesterday. Okay, so I was telling you yesterday that we have studied already about or we have analyzed an MM1Q using the notion or assuming that it is an exponential distributed arrival. Inter-arrival times are exponentially distributed, and then from there we found out that okay, in that case the arrivals are Poisson, and then we assume that we do not assume, we just get to see that it actually follows a birth-death process. And then we get to know that okay, if it follows the birth-death process with these probability transitions, then we will get the following as the waiting time, the number of jobs that are in the system, and so on. And with the help of Little's law, we found out all the other values. Okay, what we are going to see today is that we start from the assumption of a birth-death process. That means we start from the assumption that an MM1Q can be analyzed by assuming that it follows a birth-death process, okay, or it looks like a birth-death process, and from there we will get the probability transitions, transition probabilities, and then from there we will analyze the system and we will find out the different values that we had already derived yesterday. So this is just to make you understand that either way you go, either way you assume, you are going to get to the same point. Okay, so this is just another way of deriving your or analyzing a single queue. So first of all, as I already told you, that we are assuming it as a birth-death process, and this is just the definition of a birth-death process, as I already have told you. Okay, so what do we know about it? That the state of a system can be represented by the number of jobs, that is n, in the system. Jobs will be individual arrivals, not as a batch. And if you have an arrival, then the system will go to the state n plus 1. If you have a departure, the system will go to n minus 1, causing a death. This is subject to the fact that you are currently at the nth state. Okay, so the number of jobs in such a system can therefore be modeled as a birth-death process. Alright, so this is how a birth-death process would look like. Okay, so here you are having an arrival and you are having a departure. Okay, we are not considering the situation here where you stay in the same state. Okay, just to show you that either you are having an arrival or you are having a departure here. Okay, so you have an arrival, you go to next state, you have a departure, you go to this previous state. All right, arrivals are represented as lambdas and departures are represented as mu's. So we need to first get a proof of this theorem. Okay, this also I am sure you remember yesterday, because we had found out yesterday that what is the steady state probability Pn of being in state n. Okay, and we had found this out as rho power n p0. And we had further found out other values. So today as a theorem we are going to prove this or give a proof of this, assuming that it is already a birth-death process. Okay, so this is the statement that is given here, that is the steady state probability Pn of a birth-death process being in state n is given by Pn, that is equal to lambda 0, lambda 1 to lambda n minus 1 divided by mu1, mu2 to mu n times P0. And n can vary from 1 to infinity, and P0 is the probability of being in state 0. So let us start with the proof here. Okay, so what do we assume? So we assume that, let us assume that the system is at state j at time t, which means that there are j jobs in the system at time t. Now we assume that delta t is a very small time duration such that the probability of two events occurring is 0. Okay, so that means either arrival will occur or departure will occur in the interval. Both cannot occur at the same time because delta t is pretty small. We are considering it as a very small duration. So in time delta t, so the system can move either to j plus 1 or it can move to j minus 1 at state. Okay, so with an arrival it will move to j plus 1, with a departure it will move to j minus 1 at state. Okay, so we represented it like this. Okay, the probability of one arrival, so that means it is, what is the probability that with time t plus delta t you go to the next state, that is j plus 1, given that your current state is j. Okay, so that is equal to the probability of one arrival in time delta t, and that is given by lambda j times delta t. Okay, and if you have a departure, then the probability that within time t plus delta t you go to state j minus 1, given that you are currently at state j, that is equal to the probability of one departure in time delta t, and that is given by mu j delta t. So this is the representation that we are looking at. Now if there are no arrivals or no departures, then the system will stay in state j. Okay, see, look at these values that we are having here, lambda j delta t, mu j delta t. I'm sure if you go back to yesterday's analysis, you will find out these values. Okay, these values of probability that we are getting, you will also get them there. Okay, except one fact that you have a small O delta value there, which is a very small value, negligible, and that is that is the probabilistic analysis that we have done there without assuming that it is a birth-death process. Here we are first assuming that it is a birth-death process, and we are not assuming that that O delta term here at all. Okay, so this is therefore with simple probability you will just get that if there is no departure or no arrival, then it will be simply 1 minus lambda jt minus mu j delta t. 1 minus lambda j delta t minus mu j delta t. Okay, that is the probability that there are no arrivals or no departures in the system, and the system will stay in state j. So now we have to find out that what is the probability of being in state j at time t. So we represent that by pjt, that is the probability of being in state j at time t. So first you start with the p0 delta p0 t plus delta t. So that is equal to 1 minus lambda 0 delta t p0 t. That means there has been no arrivals, but there can be a departure from state 1 to state 0. So look at this p0 t plus delta t. What are the situations in which you can stay in the 0th state? Okay, so that means you, provided that you were in the 0th state at time t. So you can either go from this state to the next state, but that will not happen because you are still staying in state 0 at the after t plus delta t. So there are no arrivals. Okay, no arrivals, but there can be a situation that you were in state 1, but there has been a departure, so it's a death. So now you will get back to 0th state. Okay, so p0 t plus delta t, that can be given by 1 minus lambda 0 delta t p0 t plus mu1 delta t p1 t. Similarly, for p1 t plus delta t, either there can be an arrival from state 0 to state 1, so that is lambda 0 delta t p0 t, or there are no arrivals or no departures at state 1, so that is given by 1 minus mu1 delta t minus lambda 1 delta t p1 t, or there has been a departure from state 2 to state 1, that is given by mu2 delta t p2 t. So like this you go on and so on when we find out that for the jth state, that is pj t plus delta t, either there is an arrival from the previous state so that you get to the jth state, so that is lambda j minus 1 delta t pj minus 1 t, or there has been no arrival or no departure at the jth state, so you are still at the jth state after time delta t, so that is 1 minus mu j delta t minus lambda j delta t pj t, or there has been a departure from the next state, that is pj plus 1 t, so that is mu j plus 1 delta t pj plus 1 t. Okay, so this is equation 1. Now we can write this pjt plus delta t minus pjt like this. When limit delta t tends to 0, so we just do the differential here, and so this is pjt plus delta t minus pjt by delta t, that is given by this term. This will be lambda jt. Okay, this is a mistake here. So this will be dpjt dt is equal to lambda j minus 1 pj minus 1 t minus mu j plus lambda j pjt plus mu j plus 1 pj plus 1 t. This you can find out yourself. This is just the differential that we are finding out. Sorry, derivative. Oof. Okay. Now under steady state, when pjt approaches a fixed value pj, that is limit t tends to infinity pjt, then it is equal to, so we know this, right? Under steady state, limit t tends to infinity pjt can be written as pj. Previous analysis, remember that. Okay, so we can write it like this, and this will imply that limit t tends to infinity dpjt dt is equal to 0. We have got dpjt dt here from equation 2. So equate it with 0 here, and then you can solve for pj plus 1. So now what do we get? Pj plus 1 is equal to mu j plus lambda j divided by, this will be mu j plus 1. Okay, this will be in subscript. Okay, this part pj minus lambda j minus 1 divided by mu j plus 1 times pj minus 1. Okay, so if you are in the first state, that is p1, you will get lambda 0 by mu1 p0. Okay, so we simply can write that the solution to this set of equations is like this. That is for pn, you will get lambda 0, lambda 1 to lambda n minus 1 p0 divided by mu1, mu2 to mu-n. So this is actually what we had started with. Okay, so we are arriving to this. Now this is equal to p0 product of j equals 0 to n minus 1 lambda j by mu j plus 1, and for any n that is equal to 1 to 2 infinite. Okay, so this is the proof of the theorem that we had started with. Now we will get to our derivations. Okay, so what we can write from there, that the probability of n jobs in the system can be given by Pn is equal to lambda by mu power n times P0 for n is equal to 1 to infinity. Lambda by mu, we know it is known as either the traffic intensity, or it is known as the service utilization, or it is also known as the service utilization factor, and it is denoted by rho. Okay, so we can write Pn is equal to rho power n P0. Okay, now this is like since all the probabilities must add to 1, the probability of 0 jobs in the system is now given by P0 is equal to 1 upon 1 plus rho square plus so on to rho power infinite. Okay, so that is, we know this from Taylor series expansion and all that. We have done yesterday how we got this. So this is, anyways, we know that this term will be equal to 1 minus rho. Okay, so P0 is equal to 1 upon 1 plus rho square plus so on to rho power infinity. That is equal to 1 minus rho. So if we put this value of equation 5 to equation 4, we will get that Pn is equal to rho power n times 1 minus rho. Okay, for n equals to 0 to infinity. So with this derivation that we have, that is Pn is equal to rho power n times 1 minus rho, now we are going to analyze an MM1Q. Okay, so I'm not getting into the basic features of MM1Q now. We have already seen it and we know by now what are the basic features if we say it is an MM1Q. So inter-arrival time is exponentially distributed, inter-arrival service distribution is exponentially distributed. Okay, and you have only one server, there is no buffer or population size limitations, and the services are happening in an FCFS manner. And because we are considering it as a birth-death process, therefore the state at which a system is defined by the number of jobs that are there in the system. Okay, and also one more thing is that in general the most commonly used queue is MM1Q because it is very easy to analyze. Okay. So it is considered as a birth-death process. So lambda n is equal to lambda and mu n is equal to mu for n is equal to 0, 1, 2, 1, so on to infinity. Okay. So probability that you have n jobs in the system, we have already derived this. This is wrong here. Okay. So this will be outside n. Okay. It is lambda by mu whole power n. This one, if you can see the mouse. So this is Pn is equal to lambda by mu whole power n times P0. This is a mistake here. Okay. So it is, so lambda by mu, we know it is the server utilization or traffic intensity, and it can be denoted as rho. So we will get Pn is equal to rho power n times P0. Okay. Rho is equal to lambda by mu. So now, yes, we know that Pn is equal to rho power n times P0. So we can write that P0 plus P1 plus P2 plus so on to infinite, that is equal to 1. So P0 is equal to 1 upon 1 plus rho square plus so on plus rho power infinite, that is equal to 1 minus rho, which gives Pn is equal to 1 minus rho times rho power n. Okay, this we have already seen. Now n is geometrically distributed. Okay, so I'm sure all of you are aware of a geometric distribution, and I have already told you earlier several times to go through distributions. So you know that what are the properties of a geometric distribution. So I will not get further into the properties of a geometric distribution. So I'm just telling here that n is geometrically distributed. You can, if you think on this, you will find out that why n is geometrically distributed. And so the utilization of this server that is the probability of having one or more jobs in the system, will be given by u is equal to 1 minus p0. Okay, so then the u will become as rho, which is why we get the server utilization factor as rho, which is given by lambda by mu. Okay, so it didn't come out just like that. Okay, anyways, lambda by mu does have a definition by itself. If you see, for a steady state, for a Q in a steady state, lambda by mu will be the server utilization factor. So yesterday when I had given you or shown you the analysis, I had shown you a graph also where as lambda by mu was tending towards 0, the waiting time was becoming much higher. Okay, so for a steady state, for a Q in a steady state, lambda should be less than mu. Okay, that's what we had seen with the graphical representation. Okay, so and this is here we get to know that why the utilization of a server is given as rho. Okay, so this is why we get to see that utilization of a server is given by rho, because it is equal to probability of having one or more jobs in the system. Okay, so this is this. Then let's get to what is the mean number of jobs in the system. Okay, so yes, mean number of jobs in the system can be given by summation of n equals to 1 to infinite npn. Okay, this will give you the mean number of jobs in the system, because Pn is the probability of having n jobs in the system, right? So from this we already know the value of Pn, we have already derived it. So put that value here, 1 minus rho times rho power n. Here n is already there and you have the summation here, and this actually gives you rho by 1 minus rho. So if you see yesterday's analysis also, you will get E of n is equal to rho by 1 minus rho. Now probability that you have more or equal to n number of jobs in the system, that is equal to summation of j equals to n to infinity pj, which is equal to summation of j equals to n to infinity, and we put the value of pj here, that is 1 minus rho times rho power j, and that gives you rho power n. Okay, so this is how we get E of n. Now to get E of t, which is the mean turnaround time, or what we call as the average amount of delay that the job will face in the queue. Okay, not in the queue, sorry, in the system. Okay, so the mean turnaround time is that the average amount of time the job spends in the system. Okay, that is given by E of t, and this can be found out. So one value you already have, that is E of n. Lambda you already know. So with the help of Little's law, you can find out that what is the value of ET. So ET will be equal to En by lambda. You already have the value of En with you, that is rho by 1 minus rho. Now this times lambda, it is divided by lambda, will give you E of t. So this is what you get here, that is ET is equal to En by lambda, that is given by this. It gives you 1 by mu minus lambda. Okay, again EW is equal to, that is the amount of time that the job spends in the queue of the system on an average. Okay, so that will be equal to what is the amount of time the job spends in the system minus the amount of time that the job spends in the server for servicing. So that is given by E of t minus 1 upon mu, and that is given by this, and it gives you rho by mu times 1 minus rho. Okay, now if you want to find out that what is the average number of jobs in the queue, then you will use Little's law. You have the value of EW with you, you have lambda with you. So ENQ by Little's law is equal to lambda times EW, and that gives you rho square by 1 minus rho. Okay, so these are the values that you get from your analysis. For doing numericals and all, we will need all of these values. Okay, and please remember, I will not give these values to you in your question paper. Okay, these are these values you should know. If not, you can derive by yourself. Okay, so please note these values very carefully and do understand how you are getting these values. Okay, I hope that because I have done this twice, they should be very clear to you by now. So can we start with a numerical today? So I am giving you a numerical here. So you have an MM1 queuing system. Okay, and the arrival rate of packets is 10,000 packets per second. That is, lambda is 10,000 packets per second. You have a Poisson arrival of packets. Packet length is exponential, and the mean size of the packets is 1000 bytes. Okay, and you have the rate of servicing. Okay, that is the rate at which the packets are getting serviced. That is 100 Mbps. Okay, so what do you need to find out? That what is the average turnaround time, that is ET. You also need to find out what is the average waiting time in the queue, that is EW. Then you have to find out average number of jobs in the system, that is E of N, and average number of jobs in the queue, that is E of NQ. Okay, so can we start doing the numerical? And after reading the question, you first tell me how would you want to start with this. Okay, what is the value of lambda and what is the value of mu? So start with this value, then we will see what to do. I will be expecting an answer from you guys. Okay, don't think that I'm just sitting here. Okay, please try to look at the question and try to answer me. What is the value of lambda here? Lambda is the arrival.
10,000. 10,000
packets per second. Okay.
packets per second.
Acha. Now, what will be the value of mu? So lambda is in packets per second. Let us have mu also in packets per second then. So what will be the value of mu then? Your server is servicing at a rate of 100 Mbps and the average packet size is 1000 bytes. So what will be the value of mu?
Ma'am, 100 Mbps divided by 1000 to 8.
Yes. What is the value that you get? Correct. So 1000 Mbps is the data rate and 1000 bytes is the average packet size. So on an, I mean, if you want to find out per second how many packets can be sent, you can find out by simply dividing it, that is 100 Mbps divided by 1000 bytes. So what is the value that you get in terms of packets per second? What is mu? Anybody?
Ma'am, 12,500.
Yes. What will be the value of rho then? Rho is the service utilization factor or server utilization factor. So that is lambda by mu. So what will be the value of rho?
0.8.
0.8. So can you tell me that whether this queue is in a steady state or not?
Yes, ma'am.
So why do we say that it is in a steady state?
The ratio is less than 1.
Yeah, so that is lambda should be less than mu. Only then we say that this kind of queue will be in a steady state. Okay, so now can we find out what are these values? That is average turnaround time, average waiting time, and average number of jobs in the system. Can we find this out? Let me put these values. Just a second. You can see my screen, right? This Word file is visible to everybody?
Yes, ma'am.
Yes, ma'am.
Okay. So so we are looking for the average turnaround time, that is E of t. So we find out E of t as 1 by mu minus lambda. Okay. So can anybody tell me what is the value of ET that you are getting?
0.4 millisecond.
0.4 millisecond.
1 by 2500.
0.4 millisecond you
And
are
then
getting.
1 by mu minus lambda. So it comes to 1 by 2500. So it is 0.4 millisecond.
Okay. Is everybody getting this similar value like this? You can also put it in microseconds or something like that if you wish to. Or milliseconds is also fine. That's not a problem. Whatever is easier. Let me know if everybody is finding this value or is there is any discrepancy, because I'm not calculating this value here right now. So EW, what will be EW? EW is the time that your system is basically, your job is basically spending in the queue. All right. So that is E of W. So how do we find out E of W? The total time that your job spends in the system minus the time that it spent to get served. Okay. So that is E of W. So I would like to get this value. Then the other value is what is the average number of jobs in the system, that is E of n. This you can get from Little's law. So E of n should be Et by, am I saying it right, or lambda Et? Yeah, lambda Et, sorry. So this is from Little's law. Then you get E of nq. So E of nq also you can get from this value. Okay. So now I would like to know what are the values that you all are getting.
E of W is 0.4 minus 0.08. It is 0.32 milliseconds.
This is Jayanti, right?
Yeah.
Yes. Okay, so only Jayanti is doing the numerical, or anybody else is not doing the numerical at all?
Ma'am, expected number of n is 4.
N is 4. And what about NQ?
3.2.
Okay, good. I am not doing the numerical. I mean, I'm not calculating any of this anyways. So I hope that it seems to be correct to me. But just check that whether you are just getting, all of you are getting the same values or not. Okay. So my job is to tell you that how to solve it. This is how you have to solve it. Okay, the solving part you can do. Just calculate what are the values. So I hope that this part is clear, how to solve this kind of a numerical. Okay, so shall I close this part? Shall I start with the next part of the presentation? Some yes or no answer would do. Is everybody done with this?
Yes, ma'am.
Yes, ma'am.
Okay. 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 All right. So yes. All right. Now let's get to the next type of queue. Okay. So we have done the simplest kind of queue as of now, that is MM1, where you had Poisson arrivals and your distribution, service time distribution was following exponential distribution. Okay. So that was the kind of queue that we were looking at, and you had only one server. Now we are looking at a variation of this kind of a queue. Okay. So see, look at the numerical here. What was told? That you have a given service rate that is 100 Mbps. Okay. But the packet length varies exponentially with mean size of 1000 bytes. So this variation was causing the variation in service times. Okay, even though your service rate is the same. All right. So this is an example of an MM1 queue for the service time distribution. Why it was M? This is the explanation of it. Now suppose in this same kind of a system, if I say as a network administrator that it's always easier to have packet size same. For example, in ATM networks, you have the same cell size, right? So what if I use that kind of a system and I give the same service rate? So then it becomes easier, na? Always the service time will be the same. Okay. So how do I analyze those kind of systems? Okay. So for those systems where packets are of fixed length, but the arrival is still following Poisson distribution. Okay. So in that case, you have less amount of waiting time. Okay. How you have less amount of waiting time? Because so this I am not deriving it. It is going to become pretty difficult if I again derive it. If you are interested, please go ahead and check in the data networks book by Gallagher, Butsekas and Gallagher, or in Rajan's book also. You will have a little bit of an easier way of analysis. So see, Butsekas and Gallagher gives you a very detailed analysis, probabilistic analysis of such systems, and Rajan gives you a very easier way of looking at such systems. Okay, it doesn't get too much into the probabilistic analysis. Okay, so I am taking just this part from Rajan's book. I'm not going into the entire detailed analysis of MD1 queue and further queues because we have less time, and also this is not exactly the part of this course. So we are using queue for something else. So I am just showing you why we are getting these values. So the most general queue that we have, that is MM1 queue, I have already shown you how to analyze that. So you will be able to analyze further systems if you want to. Okay. So now MD1 queue is said to have half the waiting time of an MM1 queue. Okay. So how do we represent the waiting time? So this waiting time, of course, is not for the entire turnaround time. Okay, this waiting time is at the queue because the server is anyways going to take a fixed amount of time for servicing for the MD1 queue. Okay, so D stands for deterministic. You already know what is the packet length. You already know what is the rate at which the server is going to serve. Okay, so therefore the service time that is actually represented as deterministic here. So that is why it is known as the MD1 queue. Its waiting time is given by half of the waiting time of an MM1 queue. Okay, so we know what is the waiting time of an MM1 queue. We have already seen. So that is given by rho by mu times 1 minus rho. Okay, so we get, after doing that et minus 1 upon mu, we will get that value. So from that we get that the average amount of time, or the expected time a job has to wait in the queue of an MD1 queue, that is given by rho by twice mu 1 minus rho. Okay, so this is EW for MD1. So from there again we can use, further derive all the other values. So ET of MD1, that is the average turnaround time for MD1 queue, would be equal to EW MD1 plus 1 upon mu. Okay, what is the time that is required to service the job? So that is equal to rho by twice mu 1 minus rho plus 1 upon mu, and then you can find out the value. Okay, so this is for an MD1 queue, and from further, using Little's law, you can find out E of n is equal to lambda t. You will get the value of E of n, and again E of nq also you will find out, because you have the value of EW and lambda with you. So lambda EW is equal to E of nq, which is equal to rho square by twice of 1 minus rho. Okay, so this is for an MD1 queue, okay, where you have same packet size, okay, or a fixed packet size here, and the service rate is already given as fixed. So the server servicing is actually deterministic. Now if you do not know what is the distribution that it is following, okay, so in that case what do we know? We generally put it as the under general distribution. Okay, so in those cases, how do you represent such a system, and how do you analyze all of these values? Okay, so suppose again you have a system where you have Poisson arrivals given by a arrival rate of lambda, but the service time, again here you do not know what is the average packet length, and it does not follow any known distribution that like exponential or Erlang or anything. Okay, so for that reason you put it as G, that is general distribution. And what do you know? What is the average service time, or what is the mean packet length? That you can find out. So that is given by E of S. So E of S represents the average service time or the mean packet length. Sigma denotes the standard deviation of the service time, and CS denotes the coefficient of variation, which is equal to sigma by E of S. Okay, so the traffic intensity or the server utilization, that is rho, is given by lambda times E of S. And we say that the system is stable if rho less than 1. This we already know. So what else do we know? That the probability of having 0 jobs in the system is given by P0 is equal to 1 minus rho. Okay, so please look at the derivation here from Rajan's book if you want to. So it is this EW value is given by rho times E of S times 1 plus CA square divided by twice of 1 minus rho. This is how we represent E of W. Now from here we can get E of N also, that is equal to rho by this is missing, rho plus rho square times 1 plus CS square, okay, divided by twice of 1 minus rho. Okay, this is my mistake, I'm sorry. Here it has to be, I mean, there was a bracket here. Okay, CS square, the close bracket is missing here. All right, so now from here we have to find out several values. Okay, now suppose you have exponential service time, that is with mean 1 upon mu, and the standard deviation is also 1 upon mu. So E of S becomes 1 upon mu. Okay, so in that case, if you put these values in EW, you will get the EW as rho by mu times 1 minus rho, because CS will become, that is coefficient of, what is CS? Coefficient of variation, which is equal to sigma by E of S. That will become 1 because both of them are having value 1 upon mu, right? So with this, if you put, you will get the MM1 system with exponential service time, which is equal to rho by mu times 1 minus rho. So basically what is being said here is that this is the general distribution CW. Okay, so when you use MM1, so this is basically the superset. All right, so from MG1 you can actually see that if you put variations, that is if you put MD1, that is everything is known to you, then also from this value of EW you can get to the EW of MD1. Or if you use exponential distribution for the service rate, service time distribution, then you will get the same EW for MM1 also, as we have already analyzed it. Okay, so this is for MG1 queues. Now this is a variation that we have, and that is for a finite system size. Okay, let's not call it as a finite buffer size, as has been written here. Of course you have a finite buffer size here, but if you have a finite buffer size, the system's capacity becomes finite here, right? That's what I mean to say here. So suppose you have an MM1 KQ, the system capacity becomes K here. Okay, so you are serving one job at a time at the server, so your buffer size becomes K minus 1, and one job can be there at the system. So you have a fixed buffer size, and your system can serve, your server can serve one job at a time. Okay, so in such kind of system, what will happen if you send a large number of packets at the same time, and if it exceeds the buffer size, then those packets will be dropped. That's what happens in your real life also with routers. We all know that. Okay, so these packets will get dropped. So essentially there will be only some amount of lambda that will reach the system, and there will be some amount of lambda that will be dropped. Okay, so all right, I think I am out of time. It's already 9:55, so I will not get further into MM1 KQ because this is a full derivation here. So tomorrow also now we will do MM1 KQ, and not tomorrow, day after tomorrow we will do MM1 KQ, and then we will start with MMMQ. Okay, that is you have M servers, and then we will do some numericals. Okay, so this is going to be interesting. So I hope that you guys understood today's class well.